Okay, this is the astronaut training problem, and it says, during training, astronauts practice experiencing high accelerations like the ones they may experience in their missions. Part of this training involves being whirled rapidly in a circle with a radius of 5 meters at a constant speed. Okay, so we've got our circle-ish, and we've got a radius that is 5 meters. And we've got constant speed for our astronaut, which is, say, here, or who is, say, there. Part A, what is the tangential speed required to achieve a 5g acceleration, and in what direction is this acceleration? Okay, well, if they're moving at a constant speed around a circle, then that's uniform circular motion, and we know that there's an acceleration that's towards the center of the circle. Okay, so that's the answer to the latter part of that. So that's the direction of the acceleration. And then we just need to calculate what that tangential speed to get this acceleration would be. We have an equation for centripetal acceleration, which is this. And we know that the desired acceleration is 5 times g, which is 9.8 meters per second squared. Multiply both sides by r, and that gives us that v squared is equal to that. And that means that the square root of all of that and then we just need to type that into our calculators, and when you do, you get something that is about 15.7 meters per second. Okay, so now for B, we're asked, if the training apparatus and the astronaut start at rest and go through 6 revolutions before achieving the tangential velocity in part A, what is the angular acceleration of the astronaut? Okay, well, we start at rest, so we want this to be equal to 0, not meters per second, sorry, rads per second. Okay, and our final angular speed, well, we would actually need to figure that out. So we know that it's going to be the equivalent of this tangential speed, right? So remember that this is a tangential speed here. So we can apply an equation to that to figure out what it is, right? Because that's the speed that they're going to achieve. It's just equal to this. And this is 3.13 rads per second. All right, so we have final angular velocity and initial angular velocity. And all we have left in terms of our knowns is the angular displacement, which is 6.00 revs, which converts to 2 pi times 6 radians, okay? Because there are 2 pi radians in a rev. Okay, then we use the following equation to solve for alpha. Alpha then is equal to difference of the squares of those 2 angular velocities. We have all of this going in. We have this for final. We have that for initial. And we have 2 pi 6 in for delta theta. If we plug all of that in, I believe you get, rounded to a few sig figs, this number. 0.130 rads per second squared. So a relatively gentle acceleration in terms of angular acceleration to get up to the final speed, though the centripetal acceleration would be getting larger and larger and larger as it accelerates. Okay, see, how would the acceleration in part A compare to the acceleration of a box sitting 2 meters from the axis of rotation? Okay, well, you can go about this a couple of different ways. One way is to rewrite the centripetal acceleration equation in terms of angular velocity. And if you do that, you get omega squared r squared over r. And so A equals omega squared r. And we know that the angular velocity of everything moving along this circle, right, because it's a rigid object, whatever he's attached to, has the same angular velocity. So we know this is 3.13 when they're up to full speed. But the radius here is considerably smaller, right? The box is sitting only 2 meters away from the center of the circle. So when we plug all of that in, okay, we get something that is about 0.4 times the value that you have in part A. And if we just, let me type it into my calculator right here. We square that, and then we multiply it by 2. And we get 19.59. So there's been some rounding error here because that is otherwise known as 2g. Okay, so there's the problem.